Hi everyone, my name is Summer,
My name is Zeroth.
And my name is Preston.
and we are here to give you a history of the thermodynamics laws and give you some applications and show you how relevant thermodynamics is to your current life. Thermodynamics is the branch of science that studies the relationship between heat and all other forms of energy. And Lord Kelvin, as we call him, and we'll go through his history later on, coined the term thermodynamics, and it's taking thermo, the heat, and turning it into energy dynamics, or the other way around. It's just their relationship. Thermodynamics is extremely relevant to our daily life and can be grouped into 4 laws, 0 through 3, and we will discuss their history now. So the development of the first and second law were around the same time, the 1840s to 1850s, by several key players who we will dive into. And it started with the big question of heat and work and if they could be equivalent in some way. Could you take heat and make it into work, or the other way around? And this was theorized by Carnot in 1824, but there was no major consensus until later in the 1840s. And the consensus began when James Joule began conducting his own experiments to prove this by having a paddle wheel do work in the water and measuring the heat in the water, measuring the temperature to see if the temperature increased, which he did. He found that the temperature did increase. And this was a huge discovery. Just being able to prove the equivalence of energy and heat was really, really big. And this experiment led to prove the conservation of energy, as we call it today, which became the first law. And there were a lot of other key players, but obviously we want to focus on the main ones for you here today. The first law was officially developed by Thomson and Clausius in 1850, and Thomson was Lord Kelvin, who I discussed earlier, but Thomson was his original name. He later was called Lord Kelvin. And key scientists and engineers disputed whether heat could be turned into other forms of energy or back and forth, but Thomson and Clausius really established this first law of thermodynamics of the equality of heat and energy in 1850. And so today, we see the first law of thermodynamics in everything we do. For example, when you eat food, it keeps you warm. So you're eating that to keep you warm. There's so many examples that you will now be able to see in your own life. Now, the second law, as we discussed earlier, was developed around the same time with several key players like Clausius. And Clausius in 1850 explained that heat cannot flow naturally by itself from a cold to hot body. And this will be then entropy later on. But he also theorized that it was impossible to fully convert heat into work, because earlier we found out that you can turn work into heat, but he theorized that heat cannot be fully transferred into work, which is accurate to this day too. And after this theory, there was a long time where many theories were rejected at this time, but Clausius continued to develop his entropy equation, and in 1854, he came up with this equation where S is entropy, Q is heat, and T is temperature. And entropy is the tendency of order to disorder in a system, like we explained earlier, how heat flows from hot to cold and not cold to hot. This is what entropy is explaining.
So after the first and second laws were developed, the third law was developed over a period of 1906 to 1912. So as the study of thermodynamics continued to grow, James Clerk Maxwell published the theory of heat, which was a fundamental piece of text in 1871. This theory of heat that Maxwell wrote about laid out the fundamentals of thermodynamics clearly and simply enough for a beginner student to understand, which paved the way for the future of thermodynamics. So in this theory, he lays out the ideas of kinetic theory and his ideas on the second law of thermodynamics. So as these ideas were passed around the community and puzzled about between many different men, Boltzmann realized around 1876 that gases have more chaotic states than orderly states, and he came to make a connection between entropy and molecular motion, which is shown in the equation below, where S is entropy, K is Boltzmann's constant, and W is the number of states available to the system. So after all of the first three laws were developed, the idea of heat was still like a pretty ambiguous topic. So in order to understand what the zeroth law is, we need to understand what heat is. So until the mid 17th century, like I said, temperature was very ambiguous since there was no way to develop a quantitative measure of heat. This idea led to like the development of a thermometer, as well as many different men inputting their ideas, such as Celsius and Lord Kelvin. So this idea led to a development of a way to measure heat, which was named after Celsius, which was a more practical way to measure heat. However, this way of measuring heat was hard to use in most thermodynamic equations. So it led to a way of measuring temperature called Rankine, which assumes an absolute scale of temperature based on a lower limit of zero, which is easy to apply in our thermodynamic equations. So this idea of temperature led to the idea of the zeroth law. So what is the zeroth law? It became official in 1930 after it was coined by Ralph Fowler. And so this idea of the zeroth law is the phenomena that two bodies can have the exact same temperature, which was actually not even realized until around 1871 by James Maxwell in his heat theory, which I talked about earlier. So the zeroth law can be described as two bodies, each in thermal equilibrium with a third body, are in thermal equilibrium with each other. So basically that means like if two bodies are going to have the same temperature, they're going to match the temperature of the other body. So it's named the zeroth law because scientists did not want to undermine and confuse the naming convention of the laws that had been in existence already, since it was coined in the 1930s. So they named it the zeroth law because of its basic character.
Now that we learned about the history of the different kinds of laws of thermodynamics, now we're going to be focusing more about the applications and the history of it. The related examples of the applications of the laws of thermodynamics would be jet engines, rockets, general engines, refrigerators, and other things that could relate to the first law and second law and third law and the zero law. First, we will be focusing on jet engines, which it came into history in 1913, where Brandon Loren, aerospace engineer, designed the first ramjet. And in 1930s, engineers realized that the maximum performance of piston engines was limited, and the idea of jet engines came into just an idea during that time until 1937. In 1941, Frank Whittle had invented a first-class power unit for aircraft proportions. And the current process, a jet engine is used to provide the jet propulsion to power aircraft because they can produce very large power per unit engine weight, which is being applied for the first and second law since it's a open and closed system. Now, we'll be talking about space rockets. And the space rockets didn't come about until October 4th, 1957, or even earlier beyond, but it was just an idea until they made it work. And Soviet Union was one of the first um, agencies that launched the first artificial satellite and also started a space race against the United States. In January 31st, 1958, the Jupiter C was the first successful space vehicle launched from American soil by a German engineer. The current process is a chemical rocket works by burning the fuel and oxidizer in a combustion chamber, which generates a high pressure and high temperature, which is being applied for the first law and has a constant entropy, which was mentioned a lot during our presentation. Lord Kelvin published an article in 1849 discussing steam engines, which takes heat and transfer it into motion. Also, a group of engineers came together to engineer the four-stroke cycle engine in 1876, along with Carl Benz, which he engineered a two-stroke cycle engine in 1878, which the current process is. Engines is a heat system that converts heat or thermal energy to mechanical energy, in which is converted to work, which is being applied for the first and second law. Refrigerators also came into discovery by William Cullen in 1748. Oliver Evan designed the first refrigeration machine that used vapor instead of liquid in 1805. And the current process of which a refrigerator causes heat to flow from cold to hot by inputting work, which cools the space inside the refrigerator.
So why do you care about all this? Well, thermodynamics has greatly impacted your life. And without thermodynamics, you wouldn't have light in your home, your refrigerator, be able to travel on airplanes, any satellite TV, internet, anything. And so thermodynamics is super relevant to you. And I hope that because of this presentation, you get to see it more in your day-to-day life. And thank you for watching our presentation.